Kun from UCSD, and I will be the proxy presenter for this talk, and later Dan Yang, the first author, will be in charge of the Q&A session. So the title of the work is Motion Inspires Notion, Self-supervised Visual-LiDAR Fusion for Environment Depth Estimation. So environment depth estimation aims to obtain geometric relations of surrounding objects from 2D images. It usually generates a depth map for each 2D image, and the depth map contains the distance information of image pixels associated with real objects. Depth estimation can enhance environmental perception of intelligent machines, which lie at the heart of numerous applications, such as real-time navigation, obstacle avoidance, and dense mapping. According to recent reports, wrongly estimating the depths of the pedestrians and obstacles caused the most auto driving accidents in the past 2 years. The current depth estimation solutions typically combine camera and LiDAR to complement their strengths. Compared to standalone visual approaches, LiDAR could provide accurate 3D locations of reflection points or point clouds, and provide the scale information which monocular cameras don't have. To fully exploit both sensors, the SOTA Visual-LiDAR fusion approaches design deep neural networks as depth map generators. They take 2D visual images and associated LiDAR point clouds as input and generate the depth of the environment. Although current solutions achieve great performance, they primarily rely on high quality but expensive LiDARs. For example, the mechanical spinning LiDAR, the Validim VLP-16, costs around $4,000. In contrast, due to the limited budget, most vehicles are equipped with cheap and poor quality LiDAR. For example, the solid-state LiDAR Levox Mid-40 costs only $500, but it can only generate one-third as many points as the VLP-16, and it also suffers from a narrower field of view. With more sparse and irregular point clouds generated by low-quality LiDAR, the depth estimation performance of existing approaches degrades significantly. As shown in the second column, the estimation accuracy of the supervised learning method is reduced by 50% when using low-quality LiDAR. As a result, segmenting the sculptures and the vehicles in these figures are almost impossible. Besides, supervised learning solutions require pixel-level training data to train the depth map generator. It leads to high labor cost and system overhead. Although some recent works have proposed self-supervised learning method to reduce the training cost, these models, the performance of these models also degrades in real environment. So compared to the depth maps of the ideal static scenes, the estimation errors expand dramatically when the model co-starts in more complex dynamic environments. To solve the above two challenges, we propose LeoVR, a self-supervised solution that enables accurate depth estimation by fusing the camera and the LiDAR signals. The key insights of LeoVR is that the motion of vehicles can inspire the notion of depth maps. I'll use an example to explain this idea. So as shown in the figure, at the moment Ti, the model generates a depth map Di using the camera and the LiDAR input. Then at the next moment, Tj, the model can generate a depth map Dj based on the next input. But Dj can also be inferred from the previous depth map Di, given the vehicle motion information between the two frames. So these spatial temporal constraints can be used to further optimize the depth maps. It can also help identify reliable pixel-level training data to train the depth map generator. And this key insight brings the two key design components of LeoVR, the learning embedded motion-aware optimization scheme and the motion-optical flow instructed self-supervised framework. So first, I will introduce the learning embedded motion-aware optimization scheme. The scheme takes as input the initial depth map from the depth map generator. It then refines the depth map by optimization under motion-aware constraints. We use a factor graph to model the optimization to jointly optimize the depths, the vehicle's pulse, and the feature points locations. The factor graph consists of two types of nodes. The variable nodes indicate the parameters to be optimized, such as vehicle's pulse and the locations of feature points. And the factor nodes represent the probability relationship between these parameters. And there are two types of factors. A point factor, as the blue dots in the figure, associates a pulse with a feature point. And the depth factor, as the red dot in the figure, associates a pair of successive depth maps. We then optimize all variable nodes simultaneously to obtain the global optimal results. Next, I will talk about the details of these motion-aware factors. So the first point factor is the visual reprojection error. It optimizes the vehicle pulses and the location of 3D feature points. The reprojection error is illustrated in the right figure. So given the 3D feature point PK detected from the previous frame IJ, we can find its corresponding 2D detection PKI on the current camera image II. Meanwhile, we can also reproject PK on the camera image II and obtain the projection point pi, given the current camera pulse theta I. The reprojection error is the distance between PKI and pi, and it indicates the estimation errors of the 3D point PK and the camera pulse theta I. The second point factor is a constraint provided by LiDAR. So we project all the 3D LiDAR points onto the camera image and find the one closest to the feature point PKI, that is LK in the right figure. The deviation between the LiDAR projection and the feature point is calculated. Same as the first point factor, this point factor also indicates the estimation errors of 3D point PK and the camera pulse theta I. Then to fully exploit the initial depth map generated by the depth map generator and further optimize the depths in a fine-grained manner, we adopt the geometric consistency of the depths from different views as a constraint. So given two moments I and J, we can project the depth map dj to the view theta I based on the relative post-transformation matrix Tij. When the sampling interval between two consecutive frames is short, the depth map di and the warped depth map dj2i should be consistent. We then calculate the deviation between the two depth maps as a third constraint, and this constraint ensures the consistency of the depth maps estimated from a continuously moving vehicle. And then I will talk about the self-supervised framework of Leo VR. This framework reduces annotation cost for training the depth map generator. And it exploits the camera's motion information to automatically extract supervision signals to train the generator. And specifically, given the current image, the last image, the depth map output from the depth map generator, and the interframe motion, we can inversely warp the last image to the view of the current image and generate a warped version of the last image. Then the pixel level photometric differences between the current and the warped images can serve as supervision signals. However, this photometric projection assumes a static rigid environment, but the real environment with high dynamics hardly satisfies this assumption. So to overcome this challenge, we propose a motion-optical flow consistency constraint. The key idea behind this constraint is to select static rigid pixels instead of the whole image for training. From the geometric perspective, for a static object, its projection on the nearby frame should fall on the epipolar line, as shown in this figure. In contrast, for the moving object, their projections are unlikely to fall on the epipolar line. Therefore, we can filter out moving pixels based on this criterion, and specifically, this deviation from epipolar line can be modeled by the optical flow field between adjacent frames. And these figures show two real-world scenarios that degrade self-supervised training performance. And the left figures show consecutive frames collected by a moving vehicle, and the top right figure shows the visualized optical flow field between two frames. And the last figure shows the confidence mask. The pixels in the dark region of the confidence mask will be filtered out and won't be used to train the model. And this example shows that LeoVR can effectively filter out bad data due to occlusion, movement, and reflection. In addition to the above photometric consistency with motion optical flow constraint, we also take full advantage of the factor graph optimization framework. Two additional losses are introduced based on the optimized 3D feature points and depth maps for better training stability and faster convergence speed. We then evaluate LeoVR in representative real-world scenarios, and these scenarios are listed in the table. The city road and campus represent outdoor scenarios, and the classrooms and office buildings represent indoor scenarios. And these scenarios include diverse spatial layouts and environmental dynamics. And the architecture of the depth map generator follows the classic and lightweight model design. And we first evaluate the depth estimation performance of LeoVR with 4 comparative systems. First, LeoVR achieves the best performance in all scenarios, and it brings significant performance gains when using different types of LiDAR, especially the low-cost, low-quality LiDAR. And when co-starting in different scenarios, LeoVR with self-supervised learning outperforms other approaches by 45%. And we further evaluate the efficiency of LeoVR. Generally, it can work with a frequency of 16 Hz, which matches the LiDAR refreshing rate. We also analyze the system's robustness in the most challenging city road scenario using commercial autonomous vehicles with low-quality LiDAR. We evaluated the impact of sensing distance, moving speed, and scene dynamics. As the vehicle speed increases, the LiDAR point cloud and visual features suffer from motion blur due to their hardware nature, and we leave the depth estimation at high speed as future work. We then conduct an ablation study to evaluate the effectiveness of the individual models of LeoVR, and we evaluate the optimization framework, motion optical flow constraint, and additional constraints. As shown in the center figure, the motion optical flow constraint can improve model performance effectively, especially in dynamic outdoor environments. In conclusion, in this paper, we propose LeoVR, the first self-supervised solution that enables commercial autonomous vehicles to generate accurate depth maps by fusing vision and low-cost LiDAR. And we provide a fresh perspective to embed a vehicle's motion information into the system framework design. And we evaluate the performance of LeoVR in 4 different scenarios across 6 months. The results demonstrate that LeoVR can significantly broaden the depth estimation capabilities, even with low-quality LiDAR. That's all about the presentation, and thank you for listening.
Thank you.